All right, so we're going to start again. So to recap a bit what we've seen in terms of API. So the core object is what we call the estimator. You instantiate it by giving it its parameters, its model parameters. You train it or fit it on data using the fit method, and it will learn the parameters that are inferred from the data. So you got two sets of parameters. One that are meter parameters that are given at instantiation. The other ones that are model parameters learned from data that are learned during the fit, and they have an underscore at the end. If you have a supervised estimator, you have a predict method to predict on new data. You might have a predict proba, something that we didn't write here, but you might have a decision function that is similar to predict proba in the sense that higher values you're more confident, but it's not scaled in any way. Basically, predict can be obtained from the decision function by thresholding it. You might have a score. So score enables you to, score takes X and Y and tells you how well the model matches this X and Y. And it's going to be useful. We're going to use it later on to choose to set parameters, to set meter parameters. If you have an unsupervised estimator, you may have a transform method, just like in the PCA, and you may have a fit transform, just like in the dict hashing transformer that we saw during the feature extraction part of the tutorial. The thing about the fit transform compared to the fit and transform is that it may be more efficient to do fit and transform in one step. All right? All right, now I want to talk a bit about regularization to tell you a bit what it is and why it's necessary. So regularization is a core aspect of machine learning, of basic machine learning. And here's an example. So we've seen the one nearest neighbor estimator. So how many errors do you expect that a one nearest neighbor learner will do on the training set? Think about the learning rule.
One goes back and predicts on the same set of trained on.
Mm-hmm.
You don't leave any out. It's going to be perfect.
Right. So on the training set, it's going to be perfect by definition. Because by definition, if you show it instances that it has already seen, well, as it has already seen them, it's going to pick them from its reference database and conclude that, well, the label is right. There's one exception to it, is if you've got several instances that have the same feature set, but a different label. But that's a corner case. All right, so what does this tell us? It tells us that evaluating the performance, the prediction performance of a machine learning model on the training set will not work. We're always underestimating the error that we're going to do on prediction if we try something on data that we've already seen. Okay? What it also tells us is that, well, it might be okay to accept errors on the training set if they decrease errors on the test set. And this is the core idea behind regularization. Because by definition, on the training set, you're underestimating your error. You don't want to minimize this error, and you might want to minimize something else. And that something else will be regularization. Okay? The more data you have in your training set, the less regularization you need. We'll cover this later. All right, I'm going to give you a small example here, and then I'm going to be looking at fitting a ninth order polynomial. So I've created here a ninth order polynomial, this nice formula. I've added noise to it, and I'm plotting this. We know it's a ninth order polynomial. I've told you this. Now we want to fit this data set. And I'm going to fit two things. I'm going to fit a fourth order polynomial and a ninth order polynomial to it. So that's a simple trick. I'm going to use a linear regression to do polynomial fit. It's just I'm going to fit a design matrix, a data matrix that's made of x, x squared, x to the third, and all the powers of x till 9. Okay? So that's fitting a ninth order polynomial. I'm going to do this for order 4 and an order 9 polynomial, and I'm going to plot this. Now, I haven't plotted the ground truth. You don't know what the ground truth is. I've shown you the formula, but I suspect that you weren't able to plot it in your head quickly. Which one do you think is more plausible in these two? The fourth order or the ninth order? How come? The ninth order has probably less errors at the end. Yeah, because it's all wiggly and strange, right?
You have more the feeling that you fit the noise.
Yeah, okay, so here overfits, yeah. So basically what's happening is we're fitting the noise, and we're capturing the noise in our model. And what our intuition tells us is that when you look at this, it seems wiggly, it seems ugly. The way we formalize it is it's more complex. It's not as simple for a certain definition of simplicity. And we tend to prefer simple explanations, simple rule. That's a fairly general idea in statistics and machine learning, is that for a certain definition of simplicity, which will depend on your use case, on your priors, you should prefer simpler rules. And we do this all the time as human beings. Now what's interesting is that the true model, ninth order polynomial, doesn't work as well as a model that's wrong. And I work with the biologists, and there's something that they have a hard time understanding. They tell me, but we know that it's a ninth order polynomial. Well, they don't say this, but they tell me, we know this. And I tell them, yeah, but don't use it. They hate it. All right. And so if we look at the ground truth, it does have this dip at the end. Still, we will still prefer, I will still prefer the blue line to the green line. Okay? So regularization is about preferring more simple models, and it is really the core of machine learning. And a big problem is, how do we choose the amount of regularization? How do we choose which regularization we use? Choosing a machine learning algorithm basically amounts to choosing the model. So a linear regression is one kind of model. It's a linear model in a certain space. And choosing the set of regularization of priors.
So what does the ground truth actually mean?
Okay, so the question was, what does the ground truth actually mean in this problem? Well, we have simulated the data, so we know how it was simulated. In general, I mean, in my problems, you don't know the ground truth, so it's a hard problem. In other problems, you might know the ground truth. So suppose you're trying to replace a very expensive but very accurate detector by a camera and machine vision on the camera, computer vision on the camera. Well, you have the ground truth because you have the expensive detector. And so then your whole problem in machine learning is going to be to make the camera work as well as the ground truth. All right, so we're going to run a small interactive demo, and it's the SVM GUI file that you should have if you cloned So you want to, actually, I can do this in the Python notebook, I think. I want to run, using Python, the SVM GUI, all right? All right, so do we all get this? Little graphical user interface. So I can add data points by clicking on it. So left or right click will create two classes, black or white. Okay, so I've added 4 data points. And then I'm going to fit on it an SVM, a support vector machine. In this case, it's a support vector classifier because it's a classification problem. And then I can add new points, new data points, and I can see the decision rule changing. Are you all there? So I've just changed a bit the type of, yeah.
So what is the solid line and the dash line?
The solid line is,
That's the decision.
yeah, that's the decision.
Not the dash.
The dashed line is the margin. So when you're doing, it's specific to support vector classification, and I'll come back to it this afternoon. It's the margin. It's basically the region in which you're accepting to have errors. And so what I just did, I'm going to clear and restart, but what I just did is I changed a bit the problem class. So here I'm going to restart. All right, and now what I'm going to do, so this is all nice. I can get 100% zero training error.
Yeah, I get 6 stop.
6 stop.
There's I looked on the GitHub, it says there's an issue saying it's only 0.14 dev.
0.14 dev.
Well, someone put an issue saying this example only works in the development version. I just commented out that line and it works.
Okay. So what line is it?
Well, it's 6 things, so it's only if you're using Python 3 that it's necessary.
Ah, yeah, okay. Okay, it's because we took the example from our dev repository, and if you want to grab the example, so if you go to the stable, so you go to Scikit-Learn.org, go to the examples, and you can find the example that works on stable. That's something we keep doing. We keep doing things that work on dev because we're working on that. But yeah, I think you can probably comment out the line that's crashing. It's just there for Python 3 compatibility. So I'll give you a moment to comment that line.
The one that has 6 stop nodes on there.
Yeah. Yeah, the one that has 6, the import that has 6.
Wow, this is cool.
All right, so then you can play with it. And you can try to get something like I have. And what I have here is data that is completely separable in the training set. And what I'm going to do is I've just created data that is not separable in the training set.
How do you add the black hat?
It's going to be a right click. Got left and right clicks. And I'm not going to go over this example in detail because we're going to cover things like this this afternoon when we talk about SVMs. But you also have all the parameters of the SVM that you can play with. And you can do more complex stuff.
If you go into the X11 preferences and enable 3-button mouse, then you can use options there. In what preferences? On the X11. If you're using on the Mac, you use X11. You go to the preferences and enable the 3-button mouse thing, and then you can use options. But
So are people able to play with it? So this is just to give you an intuition of what the problem is for the learner, because The learner, the estimator, has fitted a model on trained data, and each time you're adding a new point, you're basically being the opponent. You're the test set. And if you add new points in a completely random way, there is no way that the algorithm will get there. If you add new point with a logic, the algorithm will try to get this logic. And what it will get of the logic is conditioned by the model space that it has. So if your model space is linear here, well, it's going to try to fit a separating hyperplane. So if I keep adding points that are consistent with a separating hyperplane, it doesn't have to change. And to come back to the dashed line, as long as I'm adding points outside of the dashed line, it's not changing. That's a specific thing about the SVM. So I can add points here. It's always happy. And then I can add points here. It has to adjust. Okay? And I can change my model space, and I change my model space by changing this parameter, which I will not describe here. And then it's fitting a more complex model. What should immediately pop into your mind is, hey, more complex model may mean fitting noise. Just like with the 4th order versus 9th order. So that really depends on the amount of data you have and the amount of noise. All right?
Can you show what the coefficients are in the model? Or?
I don't think so, no. Well, linear SVMs do. Yeah. Yeah. No, I kind of disagree with you. SVMs do. They have a coefficient in dual. Yeah, but yeah, so coefficients, so I mean, this is an interesting question because coefficients have an easy meaning only for linear models, but linear SVMs are linear models. All right? So I'm going to set this aside and move on in the interest of time, but you can keep playing with this, and if you stick around for the afternoon session and we go over SVMs, you can come back and develop your intuitions about SVMs here. All right. So this is a, yeah, you probably cannot read, but that's fine. This is a flowchart of how you might find your way around given a specific problem in the set of Scikit-Learn estimators. It was indeed made by a Scikit-Learn contributor, well, the most active one, Andy Miller. Not by me, so it doesn't show my own biases, but I thought it was interesting. So people go to a machine learning conference with something like this, put it up a screen, and then watch, and I'm sure you're going to have a fight in the room. And so you start, and the first question you ask yourself is, do I have more than 50 samples? No, acquire more data. I'd love to tell this to the people I work with, because quite often they walk in my room with less than 50 samples. And I do tell them this, but it doesn't work. Then the question is, am I predicting a category or a continuous variable? If I'm predicting a category, then I have a classification problem. And if I'm predicting a continuous variable, then I have a regression problem. And yeah, if I don't know what my labels are, then yeah, I'm reading it wrong. If I'm predicting a category, then I go to label data. If I'm not predicting category, then I go to quantity. In label data, if I know what my labels are, I'm going to be doing classification, this area. If I don't know, I'm going to be doing clustering. If I'm predicting a quantity, and I know what quantity I'm predicting, so supervised learning, it's going to be a regression. And if I don't know, Andy has basically summarize this to two-dimensional reduction. Though there's another option is that you're looking at predicting structure. And Andy's conclusion on this is tough luck. There are tools for this. We don't have them in Scikit-Learn, and it's probably still an area of research. And then you can dig in more details, and depending on how much data you have, whether you believe that your a problem is linearly separable or not, whether you believe that many or few features are important, you're going to be using specific learners.
So one thing is this similar to, do we have to do similar steps that we do in like traditional statistics, like looking for normality, equal variances, things like that, with a lot of our machine learning?
So the question is, do we have to do traditional steps that we do in normal statistics, like looking for normality, equal variance in our data? The answer is yes and no. I mean, there's no big difference between learning and statistics. So in a sense, if I know the statistics of your problem, I know which learner to use. Now, machine learning is often interested in situations where the number of features compared to the number of samples I mean, the number of samples is not big compared to the number of features. So the amount of conclusions that you can come on the statistical property of your data is fairly limited. So quite often, it's useful to know this, but your actual goal is prediction, so you're going to be measuring prediction error. Usually they go together. If you understand the statistical model that is behind a learner, which requires a bit more work, then you understand the statistical assumptions, and usually you want to use a learner that fits with the statistical assumptions. That's the.
Actually, so machine learning can come in handy when you have a lot more features compared to statistical models.
Yeah, I mean, for me, machine learning and statistics are just a continuum. It's just that most often machine learning is interested in high-dimensional problems. And
could you be in kind of both areas? Could you be predicting a category which would get you back into predicting a quantity based on the category you're in? I mean, could you be kind of in two places at once?
you could. For instance, there is the what's known as a ranking problem. So I have 6 categories. They're not, I just know that 2 is bigger than 1, 3 is bigger than 2. I could have this, say, in cognitive science where I know that some tasks are harder than others, but I really cannot tell the gap between the 2. Or I could have this in search engine where I would just want my first results to be the best ones, and even though there isn't really a regression model behind this. So that would be a ranking problem. We don't have so far ranking algorithms in the Scikit-Learn, but if you Google up, you'll find a few blog posts that show you how you can build ranking estimators using Scikit-Learn estimators. So that's the thing about Scikit-Learn is if you know what you're doing, you can quite often fairly easily adapt it to a new problem. So you've got to know what you're doing, know what the name of the new problem is.
I asked you this earlier, PCA is an unsupervised learning method. PLS, when you have an X array and a Y array, does that then make it a supervised?
Yeah, PLS is a supervised learning problem.
How would you put it in this chart?
So the question is, PLS, partial least square, is you've got a multivariate X and multivariate Y in general, and where would we put it in this chart? I would put it as a multivariate output regression, so I would put it in regression, partially square in regression. Yeah. That's another distinction, is that you may be working with multiple output variables, either trying to predict several classes, for instance, or trying to predict several continuous variables, and some algorithms will perform better. And better might mean better in terms of prediction performance or better in terms of computation. Some algorithm might just need to, if you've got, you're predicting 6 output variables, they might just fit independently, the 6. And some might do something better. In general, most algorithms do not support multiple outputs. So it means you just have to write a for loop. All right. We're going to move on, and what's the next? Supervised learning.
We've been through a lot of the basic concepts today about different supervised learning problems. And as we move forward, we're going to basically be building on that and kind of adding some interesting pieces and some kind of real world things to that. So right now, I'm going to talk a little bit more in depth about a classification problem and a regression problem. And we're going to move from the place of just kind of visualizing qualitatively what's going on with our models and think about how to quantitatively answer the question of how well our models are performing. And this will lead later on into things like cross-validation and model selection, which are the real core of what you do as a machine learning practitioner. So let's pull up this 4.1 right here, supervised classification. This is going back to the handwritten digits that we've seen before, but we're going to, here, instead of just visualizing the digits, we're actually going to use an estimator to do automated learning on them. So as before, we'll load the digits, and we'll activate the inline mode of PyLab for the plots. And I just copied this code from the previous notebook when, I think that name is wrong, but the previous notebook where we looked at the digits, we plotted them this way and kind of viewed what they have. And recall what we have are about 1,800 digits, each with 64 features, and those features are the pixel values in the grid. So I have them plotted here with the true value in the bottom corner. So one thing that's interesting is using some of the stuff that Gaël talked about, the PCA and other methods, to do some visualizations of the data. And we, just as we did with the iris data, we plotted the PCA, the projected version, and kind of asked how well are these clusters differentiated given these features. And in the iris, we saw the three clusters, one was out by itself, but the others were kind of combined. So we can do the same sort of thing with the digits. And here we'll use randomized PCA. It's a little bit faster. It's a non-exact, it's an approximation of PCA that runs a little bit more quickly. But for visualization purposes, it can often be really good. So we'll project down to two components as we did with the iris data. And then we apply the fit transform to the digits data once again. And if we scatter these first two components and say the color is the digit target, then we can kind of visualize what the data set looks like. So this is interesting. If you look, let me make this a little bit bigger. So we can zoom in. Yeah, if you look at this plot, you can see that the very dark blue at the bottom and the slightly less dark blue at the top, those are the zeros at the bottom and the ones at the top. And it's interesting that the zeros and the ones are in completely different parts of this parameter space. So this tells you that given a handwritten 0 and a handwritten 1, your algorithm should be very, very good at telling them apart. Now it gets a little harder with other things. The 8 and the 6 are kind of in the same region here. Is that the 8 or the 6? No, the 6 is here. The 8 and the 9 are kind of in the same place. They're both curly things with loops in them, right? So this just gives you an idea. It's not really a pre-processing step in this case. It's a visualization step. It just gives you an idea of what your data set looks like. And doing something like this when you're presented with a new data set, doing this sort of visualization can be pretty helpful just to kind of give you an idea of what you can expect from your learning algorithm. There are other dimensionality reduction methods that we'll talk about more in detail later. That's the problem. If I zoom in, these things turn into their own little boxes. Yeah, well. I'm going to have to zoom out a little bit. Yeah, so we'll look at this right now. This is the ISOMAP algorithm. It stands for isometric mapping, and it's one of these manifold learning algorithms that is similar to PCA in that it does dimensionality reduction. It reduces from a large number of dimensions down to a few. But instead of being a linear model, it's a nonlinear model, and it can capture features that PCA is unable to. So if we run this projection here, it takes a little bit longer because it's a more complicated algorithm, and scatter the results, we see another view of this, and this is interesting. When we look at the nonlinear features, it's the 4s and the 0s that are kind of separate all by themselves. And again, it's just another way to visualize the data, another projection we can use to understand what's going on with our data sets. And this is something that I do often in astronomy. I'm an astronomer. When I have a new astronomy data set, I try to visualize them in this way just to understand what was going on. And actually, my first paper in astronomy was doing manifold learning on spectral data. So I like this manifold stuff.
I couldn't remember if you talked about this at all before. How do you picking the number of neighbors?
Oh yeah, so
I was just playing with it, picking some different numbers, and you would see different sorts of clustering.
right. The question is, how do you pick the number of neighbors? And it's absolutely true that as you change the number of neighbors, the clustering changes. So if we, instead of neighbors equals 5, if we do neighbors equals 15, let's see what comes out. This is kind of one of the unsolved problems in manifold learning. It's why people like Gaël will tell you that he doesn't trust manifold learning, and he doesn't trust any results based on it, because there's not really any good, there's not really any solid metrics to decide what the best number of neighbors are.
2, it looks cool. I'm serious. You should try
2? Okay, we'll do 2. And while I do 2, what was the question over here?
Before we have dimensionality reduction, before we had the dimensionality reduction in a package called decomposition, and now we have the one in manifold. So
Yeah.
how do I find where to go?
Yeah, it's a good question. He was asking, it was in decompositions. Now the algorithms are in manifold. Probably, I don't know, that's an organizational choice that we made. All the manifold learning algorithms are here, and all the other linear ones are there, but there's some exceptions.
Well, people could claim that a PCA is a manifold learning. The problem is that there is not one way of sorting out the machine learning algorithms, and depending from your religion, you might organize things differently.
So what is manifold learning then?
So manifold learning, do you recall the S-curve that we showed before?
Yeah.
It's an idea where you have basically a two-dimensional piece of paper that you're curling around through space. It comes from topology, where you're basically saying that we have this low-dimensional manifold, which might be a plane or a higher dimensional generalization of that, that's embedded in a high-dimensional space.
Also, you fit.
So we're taking,
Topology too.
yeah, we're trying to take this sampled topology and fit it to a lower dimension. So again, we'll go into that a little bit later. I like this too. That was a good one. So this is why manifold learning is fun, because you can just start doing weird stuff. Yeah. Yeah.
On the PCA chart that you had up earlier, the x-axis is T1 and the y-axis is T2.
Mhm.
What would be on the x and y-axis with this manifold?
Okay, great question. He's asking, what do the x and y axis mean for manifold learning? And like the number of neighbors, this is the other problem with manifold learning. There's no answer. No one really knows how to interpret the axes. And I've searched for solutions for this, and it's, everyone in the literature puts it in their conclusion under future work. So so manifold learning is very interesting for visualizing your data. Maybe not with one neighbor here, but if we go back to our 5-neighbor example, we can definitely get a sense of the relationship between all the pieces of data, and we can get a sense that 4 and 0 are distinct from the rest here. But beyond that, it's hard to draw any quantitative conclusions from it.
You can do PCA regression. Can you do
Right.
regression with manifold?
Well, with PCA, you can reconstruct the components as a linear sum of the principal components. With manifold learning, you can't really do that. There are some newer algorithms out there where people claim to have been able to do that, but I haven't seen any solid results from them yet. So yeah, think of manifold learning as a good visualization tool, but it's probably good to be suspicious of anything beyond that.
When you see an image like that and things are kind of clustered do anything? Can you interpret that somehow?
Can you interpret that? That's a great question. It means that there's a place in this 64-dimensional parameter space where no digits lie. And it makes sense, right? Because digits are very structured. They have loops and you know, I'll quote Doc Brown from Back to the Future. You're not thinking 64-dimensionally. If you could wrap your mind around those 64 dimensions, it might make a little bit more sense, and you might be able to interpret that better. So let's move on from this. You know, manifold learning is a fun thing. We'll come back to that later in the second session with a few more methods that are available. But let's look at classification of these digits. What we're going to use here is something called the Gaussian naive Bayes classifier. And essentially what this does is it fits an n-dimensional Gaussian to each set of inputs. So it's a very, very stupid model. It doesn't give you good results, but it's nice because it runs really, really fast, even on extremely large data sets. So it's often the thing that I run first when I have a classification problem, because it'll run like that, and it'll give you some results that you know are not the best, but it gives you sort of a baseline where you can improve from. So the other thing we're going to do here is we're going to use this cross-validation tool called this train test split. And what this does is splits our data into two different sets, one of which we're going to train the model on, and one of which we're going to test the output on. We're going to get into some more quantitative tests here. So the train test split we call this way. We'll just, we pass in the digits data and the digits target, and we get out an X train, an X test, and a Y train, and a Y test. So let's, oops, I forgot to import here. If we run that, what we've done is we've instantiated Gaussian naive Bayes, we've fitted on the training data, we predicted it on the testing data, so that the algorithm hasn't seen this testing data yet. And then we look at the expected value. And if we plot, if we visualize the results here, this is the same thing we've looked at before, except we're coloring it green if the predicted value was correct, and we're coloring it red if the predicted value was wrong. Yeah.
The splitting of the data into training and validation, is that Gaussian? Is it just kind of a Gaussian split? Or do you just
yeah, the question was the splitting of the data. Is it a random process? And yeah, it is. There's a random sampling of the data into two sections. And this, again, is kind of a preview of what's going to come when we talk about cross-validation. But if we look at this, we can see that the Gaussian naive Bayes, even though it's not the most sophisticated estimator, does a pretty good job, right? I zoomed in too far, I guess. Does a pretty good job. Most of these digits, it's actually classifying correct. You can see a few. This one, it said it was 5, but it's not a 5. I don't even know what that is.
Resize the fonts to the normal size.
How do I do that?
Yeah, but then the image itself, with a little drag, it's a
Oh, that's a great point. Okay.
And then double click to go back to the original size.
Oh, thank you. Yeah, so if we're looking at this, we can see that there are a few of these red digits where the classifier got it wrong. Most of them, like this, you could see why it would mistake it for a 5. Oh, yeah?
When do we have different results?
That's true. Yeah.
Yeah, because it's splitting it up.
Yeah, so the train test split did a random sampling, and that means that if you're running it on your own, you'll see a different training and testing split than you're seeing from me up here. And that would lead to different results. But the point is that we're seeing that, I don't know, I'd estimate maybe 70% of these are classified correctly. Yeah, Jason?
Yeah, so this data set is currently using these images in an 8x8. Are the raw images available? Could we try this with like a higher sample or maybe like a lower sample? If you wanted to do like 16 by 16.
The question is if there are higher resolution images of these available. Not within Scikit-Learn, but I would search around online Handwriting recognition is a common enough task that I'm sure you could find larger data sets out here. There.
Jake?
Yes.
Actually, in Scikit-Learn dataset, there is a feature for ML data, which is a website, mldata.org, that has the MNIST digit dataset that is higher resolution than those. So you can use fetch ML data for MNIST, and if you Google it, you will find examples.
Great, thanks. Fetch ML data. Learn something new every day. So when we look at this, it's nice to be able to visualize this stuff, but as we move forward, we're going to want some sort of quantitative measure of how well we're doing. And these are, the sort of quantitative measure you might do is just asking how many of the predicted equal the expected, right? And you print the total number of those. So we have 354 matches out of 450 test cases. And you might even, divide one by the other and find out that you're 78% accurate. So that's a nice metric, but there are some metrics out there that are more interesting. For example, we want to know, did we confuse 8s for 1s or did we confuse 8s for 6s? That sort of information. And depending on what you want your application of the learner is, different metrics might be more important to your final result. So in the Scikit-Learn metrics submodule, there are a number of these. And one good one to do is the classification report. This actually prints a formatted table of the precision, the recall, the F1 score, and the support for each of the digits. So the precision basically says how precise you are for each 0. I'm gonna mess this up. I always mistake precision and recall when I try to explain it in real time. But it's basically, they measure how precise you are given your true value, how many of those you label correctly. And the F1 score kind of combines the precision and recall into one nice little score. So we've done the 0s really, really well, we can see here. We've done the 9s not very well on average, and in total we have this F1 score of 0.8 or so. So like I said, this is not very good. The Gaussian naive Bayes model is not great in most circumstances, but it's a good baseline to say, with the easiest, fastest, simplest classifier in some senses, we've gotten an F1 score of 0.8. Another metric that's useful is a confusion matrix. We basically print a graph of, given the input, how likely are we to call it a certain output. So the diagonal, if all the numbers were on the diagonal here, that would be a perfect confusion matrix, right? But we have some that are off diagonal, and in particular, it looks like the 1s, the 2s, and the 3s are being labeled as 8s right here. And the 9s, in some cases, are being labeled as 8s. So these metrics will give you a more quantitative idea of what might be going wrong with your classifiers. Okay, questions right now? What was the difference between precision and recall? Yeah, who can explain that well? Because I always stumble over my words when I try to do that. Do you?
Okay, precision is a way to quantify the fact that what you predict is correct, that you are not making mistakes on positive examples. And recall is a way to quantify your ability to find all the positive examples from your data set. You are not missing a positive classification.
So am I right in saying that the 9, because it's 0.96 precision, that means everything that we call a 9, 96% of things that we call 9 with our classifiers are correct. And the recall means that out of all the real 9s in the data set, we're only correctly labeling 50% of them. Did I get that?
Yeah, that's
Yep.
exactly it. T1, T2 errors.
Yeah, false positive, false negative, yeah.
So when I read this, confusion
Mm-hmm.
And then, so you said that 8s are often mislabeled as 1, 2, 3, and 9. So it would give a kind of rank. Then, if I look down that column for 8, which is the second to the right, 8s are often labeled 8s correctly, but then the next most one would be 2.
Right, right. You could, yeah, so you can introspect on, or you can look into this confusion matrix and kind of get an idea of what things are being confused. And the aggregates, kind of the average over all the columns are, in a sense, what's being shown in this precision and recall. So it's just a way to quantify your models and determine what's going on. And again, the important part of this is that we do this train test split. And we'll see this a little bit later. Because if we train on the same data we're testing on, then like Gaël showed, if you just have a nearest neighbor classifier with k equals 1, you'll be perfect every time, right? Because you're memorizing your data, and your algorithm is just spitting back the labels that you put in. So it's important to do this sort of train test split. So this was classification. Let's move on to looking at regression now as well. A little bit more detailed regression problem, and then some of the quantifiable metrics that we can look at. So for this problem, what we're going to look at is the Boston data set. These are Boston house prices from several years ago. And what we have is different features of the houses that were on the market, the neighborhood they're in, the size of the house, things like that, versus the price of the house. And you might imagine this would be an interesting application for a real estate developer. You know, if you have certain features in a certain neighborhood, how much do you expect this house to sell for? And if we print the data shape and the target shape, we see that there are 506 samples. So 506, I guess, I might be wrong. Are these houses or are these neighborhoods that we're looking at here? I can't remember.
I think they're houses in different neighborhoods.
Okay. We can look at the description to remember, yeah. The average number of rooms, okay, yeah. So we're looking at houses and different features of houses. So we have 506 samples and we have 13 features of these which are contained in the data descriptor. Now if we can visualize this data quickly and just see what the histogram of house prices is. So we're just histogramming the data target, which is the price. And we see that they're somewhere between what is this, $5,000 and $50,000. So this is an old data set. Can't buy houses in Boston for that anymore. As before, we can do something where we scatter the features versus the target. I'm going to skip over that now because we did a similar exercise earlier. But let's move on to the predicting the home prices with a simple linear regression. So again, we'll use the cross-validation, the test-train split, to split us into a training set and a testing set, and run that right there. And we're going to use a simple linear regression. And in 2 dimensions, this is fitting a straight line to data, right? But as you generalize up to higher dimensions, it's fitting hyperplanes to your data. And as before, we see that it's a simple process. We instantiate the classifier, and we call fit on the training data, and that fits the model. And then we call predict on the testing data, and compare that to the expected. And in this case, we can scatter plot the predicted price versus the expected price and take a look at what we have. So with just a simple linear model then, what we've seen is that we qualitatively, you know, we don't do very well, right? There's these scatters, especially at the high numbers, we can be off by $40,000, $50,000, which is we can be off by almost 100%. So what this is telling you just qualitatively is that the linear model itself is probably not the best. There's some nonlinear features in here. There's some things that a straight line doesn't fit very well. And here I printed one quantitative measure, which is the RMS, and I did this manually here, but this can also be done using from Scikit-Learn.metrics, import mean squared error. I guess that's, we could do print mean squared error of predicted and expected. And it'll be a little bit different, yeah, because this is the root mean square, and you square that and you get the mean square. So those sorts of metrics are in scikit-learn. So for regression problems, the types of metrics you want to use are these that are built for continuous data, that kind of that look at the root mean square or the mean square deviation from your result. And that's essentially measuring how much each point varies in the up and down direction from this line of this line of perfect fit. So as a brief exercise here, we showed that the linear regression is probably not a good model for this. As a brief exercise, I'd like you to try out applying the gradient boosting regression. So this is this is an ensemble method that we'll talk about later. It's gradient boosted decision trees. But the cool thing about the scikit-learn interface is you don't really need to understand what's going on in the background to just test out a few little things. And once you've tried some things, it can help to dig in and get some more theoretical understanding to push things really to their limits. But as a first pass, all you have to do is take this gradient boosting regressor, copy this code up here, and plug it in. So I just want to give you a chance to do that right now. And this will be a preview of the decision trees that we'll see later in the second section. And if I load this and print the result, we see that the gradient boosting regressor, it improved the mean squared error by about 50%, or the root mean square error by about 50%. So those points, especially in these high up points up here, are much better, and much closer to the true value with our predicted model. So the gradient boosted decision tree did a little bit better, and you could improve this by doing something called hyperparameter estimation, which is basically tweaking the model until you get a model that's well suited to your data. That's something that's going to be covered in the afternoon session. It's a really important piece of machine learning that builds on all of this that we've seen right here.
So this just changes the slope of the line to fit it better?
It's not that it changes the slope of the line. So hyperparameter optimization would be like, for example, fitting a line versus fitting a quadratic versus fitting a cubic function. And in the gradient boosted regressor, we're not just, remember we're looking at 13 different features here, and we're looking at the input versus the output.
Surface, but if
Mhm.
Is it just really just changing
No,
the line? It's still a line, right? Or it isn't?
the first one we fit was a linear regression, and
Yeah.
that's kind of what you were saying. It's changing the slope of the hyperplane in space until it gets the best fit. This gradient boosted regressor is more complicated. It's fitting a series of decision trees, and I purposely am not going into detail about that right now because we'll cover it more later. But it's decision trees and random forests and gradient boosted forests are very powerful methods that we'll talk about more later. Yeah, Tim.
This is surely coming this afternoon, but can we get a quick look at the importance of the various variables in this?
You can, so in decision trees, you can figure out, the question was, can we look at the importance of the various variables? In decision trees, you can see the importance of the variables, but I'm not, do you know how to do that offhand really quickly? CLF dot.
Importance.
Feature importances, there they are. Yeah, so what do we draw from that? This feature right here, if we do Boston, data dot feature names. So yeah, let's do that. Let's do I equals v.argsort CLF.feature importances. So we're going to figure out which are the most important. Then we're going to go data.feature names, and we'll flip these around because we want the most important first. So the most important is RM, which I believe is the number of rooms in the house. So that tells you that, what if we put CLF.feature importances I : -1. So that tells you that about, I don't know if these are percentages, I think they are, yeah. About 20% of the information comes from the number of rooms in the house, which I guess you'd expect, right? Because bigger houses will sell for more. And then as you go from that, I think this is distance to interesting places, and I can't remember what all the codes are, but you can look at the data.descriptor to see that. Let's print that. Yeah, room is average number of rooms, yeah. So anyway, you can, with trees, you can go in and do those sorts of detailed things. So, yeah, Brian.
So I noticed that you didn't rescale the feature vectors at all.
Mm-hmm.
Do you not need to do that for regression or for these particular?
That's a good point. So he said we didn't rescale the feature vectors at all. And I hadn't thought of that. For linear regression, that's probably a good idea to do feature rescaling. For decision trees, it's not quite as much of an issue.
Yeah, for decision trees, the ranking is important, but the absolute value is not important at all. For linear regression, it's very important to scale the stuff, and it's also important to scale the target, which we didn't, to normalize it to make it look like a Gaussian, and then transform back to the original space when we predict. But we don't do it automatically so far in Scikit-Learn. Maybe we should.
Yeah, that's a good point. So those.
That might improve the root squared of the.
Yeah, you could most likely improve the linear regression that way. That's a good point. Thanks. One more question.
So are these similar to basically the F values, I guess, that we get from linear regression?
Or which?
Like F values or?
This is a little bit different. He was asking if the feature importances are similar to the F1 score. It's a different measure. I think these feature importances have to do with some entropy, some measure of information. I'm not sure of the details, but it's a detail of the random forest or the gradient boosted decision tree implementation. So
One question on
one more.
scaling. So
Yeah.
which module do you look for to look around the scale out?
The question was about scaling. So if you want to do scaling, you look at from Scikit-Learn pre-processing. Yeah, so if you do import pre-processing, then you can see what all the different scalars and preprocessors are. So we have standard scalar, all these different things, min-max scalar, other encoders. Yeah, so when you use the scalars, you want to use them train them on the training data and then project all the test data with them. And we'll talk about pipeline learning a little bit later, which is a way to mix scalars and preprocessors and different learning algorithms all together. And we'll get into that a little bit in the second afternoon session. So right now I want to move ahead and talk about measuring the performance of a predictor. And this is getting into validation and cross-validation. And I'm going to speed through this a little bit because we have about a half an hour left in this session, and we want to get to some of the Olivier's interesting stuff. Not that this isn't interesting, but this is something that's kind of fundamental to what Olivier is going to be doing. So if we again are looking at the digits neighbor set, the digits data, and we do a k-nearest neighbors classifier with n neighbors equals 1. And here, if you look at this, we're not doing the train test split, right? So if we run this, we should see what we were talking about before. The confusion matrix is perfect, right? Because we're training a one nearest neighbor model on all the data, and then we're running that data back into the model, and it returns perfect results, right? This doesn't tell us that our estimator is a perfect estimator, because if we threw new data at it, it would not be perfect, and that's why we want to do this train test split all the time. And the same thing, we just looked at the Boston house prices data set. We can do the same thing with the Boston house prices. If we look at if we use a decision tree, which is another similar in spirit to k-neighbors, and look at the data without splitting it into the train and test samples, then look at the predicted and the expected, we get a plot that looks like this. So again, it doesn't reflect how good our model is intrinsically. It just reflects the fact that our model is good at memorizing data, right? So when you're trying to evaluate model performance, this is why it's really, really important to do these things like the train, using the validation sets. So as we saw before, we have the cross-validation. If we do the digits data and the digits target, we can call it this way. And there's some arguments to the cross-validation, or to the train test split, that allow us to specify what size of test set we want. So here I said I want 25% of the data to go into the test data. So we print it, and we can see that, yeah, about 3/4 of the data is in the training data, and about 1/4 is in the testing data. Any question?
So once we do the split, and assuming part of it is tweaking those hyperparameters and getting the best model, is there any point in then going back and adding the other data back in?
That's a good question. He was asking, once we tweak our hyperparameter, once we do the split, do the cross-validation, tweak our hyperparameters, find out the best model, should you put the test data back in to kind of retrain your model on everything? And I've heard different opinions on this. Some people say yes, some people say no, and everybody seems to have very good reasons that they believe strongly. So I'm going to defer that question till later when we talk more in detail about hyperparameters, but it looks like Olivier has an answer.
Yeah. You can refit a new model on the whole data set, but you cannot make any assertion on the performance of this model because you don't have any held out data to measure the performance anymore. So it's likely to be better, slightly better, because when you add more data, you can expect that your learning algorithm is working well and improves the performance, but you cannot know how much it improved.
How stable are those algorithms? So if for some reason I have in my data set extreme outliers, can they dominate completely the estimates?
You mean the train test split? So the question was how stable are the train test split? If you have outliers, might they dominate things? And that's the reason that the train test split is randomized, to try to prevent that sort of thing. But say you have one outlier in a data set of 100. Depending on what your train test split is, you might get different performance. And that's where multiple splittings can become useful. You know, you do 10 or 20 or 100 different splits and average the results. And that's the shuffle split cross-validation.
Or you do pre-processing and you evaluate those outliers to see if they should be taken out or not.
That's true. His point was you could do some pre-processing to try to remove those outliers, and that's a valid thing as well.
So removing outliers during pre-processing is probably going to be an unsupervised task. And in our experience, and we've looked at this in my research group, it's just way harder to do removing outlier in an unsupervised way rather than an supervised way, unless they're gross outliers. So not every algorithm is equal to for outliers. Some will perform better than others. Typically, SVMs are pretty good. They handle outliers reasonably well.
I'm a Bayesian at heart, so I tend to construct a better model that accounts for outliers. But that's just me. So I'm going to run through this really quickly. Here, this is like what we've seen before. We can print the confusion matrix. And here we've used the training data, the train test split that we saw above. And we see the confusion matrix is not perfect, but interestingly enough, the one nearest neighbor here works really, really well, even when you split the training and testing data. And I'm not sure exactly why that is. It's somewhat surprising. So if you want to explore that and figure out why one nearest neighbor works so well on the digits data set, I'm not sure. And again, we can print the classification report and see how well one nearest neighbor works, even when we're using the train test split. And we saw the F1 score before. And another interesting thing is if you compute the F1 score on the training data itself, so this is showing that perfect overfitting that we got get an F1 score of 1.0. And as we'll see later when we talk about learning curves, this difference between the F1 score or the score on the testing data and the score on the training data is an indication of how your model might be overfitting or underfitting the data. So we'll come back to that a little bit later. This is a preview for later. The difference between the training scores and the testing scores are interesting. As we saw, we can do the same thing with the Boston data, right? We're loading the Boston data set, we're doing the train and the test split, and we use the decision tree regressor, and we can see that the validation error, this was the one that looked perfect above. The validation error is about 70, or 0.7, and the training error, actually this is the score. So higher is better. The validation score is around 0.7, and the training score is 1.0, or perfect. So this is showing us that there's this large split between the validation and training, so we're overfitting the model, which we'll get into later. Yeah, that's another thing it kind of depends on your data set, and people have different feelings about that. The question was, how big should your test set versus your training set be? And I'm sure Gaël and Olivier both have strong opinions on this.
It really depends on the total training size and your ability to converge to a good solution before using the complete training set. So if you have a lot of data, you can just reserve 5%. You can take a larger test set, like 50%, for instance, because the training will have converged with earlier, basically. And so you can get a finer evaluation of your performance by having a bigger test set, a more stable evaluation. If you have very few data, then you should have a very small test set and do many iterations of cross-validation to do an average that is quite stable. Because if you introduce bias by holding out data because your training set is smaller, so your performance will be smaller too.
Another question, yeah.
This number of at least 50 cases, does that count for the whole group or for each group here? Because support is sometimes less than 50.
At least 50 cases?
Yeah, we had this
flowchart.
Oh, yeah, the flowchart.
So my question is, should I look on the total number of my test cases or for each
That's just kind of, I wouldn't say that's a hard limit. That's just kind of a, a hand-waving limit.
Yeah.
So look at your total number of
It's
cases.
because in the flowchart, it was the first decision that was made before knowing whether we were doing categorization or not. But you should at least have many samples per category, because if you have no samples for a given category, you won't be able to predict anything on it.
Where many is defined as 50-ish.
Yeah, 50-ish. 1,000 is better.
Yeah. So we have an exercise here at the end. I'm gonna skip over this in the interest of time, because it's basically showing, you might enjoy going back and doing this, basically comparing 3 different classifiers and using these quantitative rubrics and determining which one is the best. And that's essentially what we're going to do in the advanced stages, is figure out what the best classifier is, or the best version of a particular classifier based on these quantitative measures of the data set. And that's what we call hyperparameter estimation that we'll get into later. Oh yeah, there's, as before, there's a solution down here, so you can take a look at this if you'd like to. So right now I'm going to bring Olivier up. We have this application to facial recognition right here, this notebook 5.1. We're going to skip over that so we can get to the text mining piece. But it's kind of a complete notebook, so if you want to go back over it later and see how we string together PCA with a classifier to do some facial recognition of George Bush and his friends, then it's kind of a fun example. Yeah, quick question. You mean once the model is trained, the prediction complexity? It really depends on the model. Every model has its own quirks in that way. But generally speaking, I'd say that the prediction complexity is much less than the training complexity.
Are there models that are equally efficient?
Yeah. Linear models are very fast because they just compute a dot product between the features and the coefficient. But for instance, there is a counterexample to some models are slower at predicting than learning. For instance, nearest neighbors. For instance, you don't do anything at fitting time in nearest neighbors. You just store the whole data set. And when you predict, you compute the distances to all the samples from the training set. So this is really just a baseline. Nearest neighbors is just a baseline to compare other. So instance-based models like nearest neighbors are really bad at predicting. Support vector machines with kernel model. They store a summary of the training set that can be big, so they can be slow at prediction. And random forest and stuff like this, it's a bit in between because they are, because of the decision tree, they store a lot of the instance of the training set, but the prediction is quite fast because it's a logarithmic between, with respect to the depth of the tree. So it depends. It really depends on the model. Okay, so the last short section for this morning is how to apply all the concepts we've seen this morning to a specific kind of problem, which is how to deal with text data. And in this specific case, we'll focus on classification, so classifying text document. So to get a feel of what we are going to do this morning, I will just show you a complete example of a typical pipeline for text classification. So here, this cell here, I need to familiarize with the trackpad and hide those guys. Okay. So here you have a complete pipeline for doing text categorization. So you can see that we import 3 components from Scikit-Learn, something to load the text files from the hard drive, something to vectorize the files into NumPy arrays, or in this case, SciPy matrices, and finally a classifier, which is a naive-based classifier in this case. So to be able to run this, you need to unzip the dataset zip file in your notebooks folder, or you need to have run the fetch data script previously. If not, it won't work. But you can just follow along because we won't have time to wait for the download now. So here I'm specifying the categories that I'm interested in. This data set that I will load is called the training newsgroup data set. It is a collection of posts that were submitted on Newsnet groups like 20 years ago. And those are 4 news groups. One is about atheism, one is about religion, another is about computer graphics, and the last one is about science and space in particular. And so we can load 2 splits of this data set, one that has been splitted by time. So the first half that we will use for training is before a specific date, and the other is after this date. And it's better to do a time-based split because it's harder to predict the future in general, because the distribution might shift a bit. So we load those 2 training sets, and then we summon the TF-IDF vectorizer, which is a component that will convert the text into SciPy sparse matrix. I will explain later how it works. And then pass this X-train and Y-train data to my classifier and compute the training score, and then transfer the test set to the same vectorizer that we created previously and used to transform the train data, and apply it on the test data and compute the test score of the classifier. So let me run this. Oops. Okay, Gaël forgot to run this. It's gonna be complicated. I completely forgot that we switched computer. Or mine.
Or yours. If yours works, it's an evil computer.
So big picture, you're looking at the naive phase versus the support vector. Seeing how
yeah, in this example, we will start with naive Bayes and then use other penalized linear models that are more similar to linear support vectors. And both of them are good baselines. Usually it depends on the size of the documents. There is a trade-off between the two. Okay, let me go back to the example. Okay, so I just ran this, and now you can see that the training score is 95% and the test score is 10% below, so it's 85. So our classification pipeline is quite good at telling apart those 4 classes just based on this historical data. So let's see a bit more in detail what we just did. So we have the raw text document as input. We have labels. Those are the names of the news groups. We used a vectorizer object to transform, to extract numerical representation of the text document. And we passed the label to the machine learning algorithm, the classifier. In this case, it's the naive Bayesian classifier. And then we apply the same transformation on new documents for which we don't have the label. And we apply the prediction model to them by calling the predict function and get the expected label. And if we compare this expected label to the true label, we can compute the score.
Are the feature vectors like things like n-grams, or do they have anything else?
Yeah, we can extract n-grams. I'll go into details now. So the data set first. So if you run the fetch data script, you should have those folders here for the train and test part. For instance, if I have a look at the train part, I can see one folder for each category. So I will just consider 4 categories out of the 20. So for instance, inside the atheism folder, I have many text files. I need to go through to be able to scroll. Oh, sorry. OK. And if I have this folder layout, which was quite common, I can use the load file utility, which will randomize the samples into a list of documents. Here I applied the load file on the complete dataset without passing any category, so I get all of them. But I could pass a specific category as I did previously and just get the samples for the 4 categories that I'm interested in. So if you have a look at the shapes of the stuff that we collected, so the first array is the target array. We have integer representation for the class. And because in Scikit-Learn we want to be very memory efficient, so we don't store the strings for the labels, so you need to convert them back to the original string if you want to interpret them. And you can check that the data attribute is actually a list that has the same number of items as the labels, the target. We can also check the type of the first element of this list, and it's a Unicode object. So the load files utility has already decoded the text files. Here I defined a small utility function to display the first post. It's from the SciElectronics category, and here is the text. So this is the label, and this is the input. So, and I have many other like this. I can also use those 2 utilities to have an idea of the global size of the training set. So it's a couple of 100 megabytes. It's 100 megabytes actually. So for the 4 categories, I just have a subset, so it's much smaller and it's faster to train on those. So now that we have the data, we can extract the features, the numerical features, the numerical representation. To do this, we will use the TF-IDF vectorizer, which is a class from the feature extraction text package. It has many, many parameters that allows to customize how we extract the features from the text. And this basically implements what we call the bag of words representation, plus the possibility to do n-grams. I'll skip the details about the n-gram stuff, but for those who know, it's able to do it. So the TF-IDF vectorizer has a simple API, which is you create it and you can pass arguments to customize it. And then you can call fit transform on the list of text documents, so a list of strings, and you will get the vectorized representation. So you can see it's quite fast. For 20 megabytes, it's 2 seconds. But it's not that fast. And what you obtain is sparse matrix. Why sparse? Because the columns of this matrix will be the individual words that occur in the whole corpus. So if you have 1 million words, unique words in your corpus, you will have 1 million columns in this matrix. But for each individual document, only a few words of the total number of possible words will be used. So most of the values in this matrix will be 0. So we don't store the 0 in memory because it will be completely useless. And we just store the location of the non-zero attributes on the non-zero values. So this is tricky because the sparse API, sometimes it feels a bit like a NumPy array, but sometimes it's different. So you have to get used to it. So I can check the size, the shape of this matrix. So I have the 2,000 samples for my 4 categories. And I can check that in the list of original text strings, Python strings that I've loaded in memory, I have the same number. So the number of rows in this matrix is the same number as the number of documents. And the number of columns is the number of unique words I have seen in this data set. So in this case is 30,000, 34,000. I can also access the vocabulary attribute of the vectorizer, which is a Python dict. And it has as many elements as columns. And in fact, this Python dict is a a way to map the words, the individual words, to a specific column. So it's the keys of this Python dict. I won't display it because it's too big. But the keys are the individual words, and the values are the column indices. So it's a way to map the words to the column. I can have a look at the first keys in this vocabulary, and you can see that there are words that are crappy because I didn't configure the regular expression of my vectorizer to get rid of them. It's a very simple regular expression.
So it's taking some of the numbers that
Yeah. Whenever there is 2 characters that are not punctuation or white spaces, it considers them as a word, 2 or more, 2 consecutive. So if I look in the middle, I get more meaningful values. So those are real words, English words. Then I can check the target of the training set. So I have a yTrain, which is the target attribute of my training set, which are the folder names, basically. So the folder names are stored in this target names attribute, and the yTrain vector is an NumPy array of integers. So we encoded the categories as integers to be more memory efficient. I can check that the xtrain first dimension is the same as the ytrain first dimension, which is the number of samples, the number of documents. So it's just a good sanity check. So now that I have my training set that has been encoded as numerical values, I can use the randomized PCA. So it's a more efficient PCA that is able to deal with sparse input and extract the first 2 principal components of this data set and plot it. And this is useful, as Jake did previously, to first, when you get new data, to plot it in 2 dimensions using a PCA to get a feel about how the different categories are organized with respect to one another. And in this case, you can see that the red and green, okay, it's not the same order. So the blue, dark blue, and light blue are atheism and religion. And you can see that they are mostly mixed in together because they share a lot of the same words. So they are projected in the same area of the space. Whereas the red stuff is for science space, which is quite alone. And in the middle, we have computer graphics. So maybe the vocabulary is not as specific as science or religion for computer graphics, and so it's more in the middle. So once we have those numerical representation, we can train a classifier. So in this case, we use the multinomial naive Bayesian classifier. It can fit X and Y on it, the training set. And we can transform the test set using the same vectorizer. This is important because we need to extract the same feature on the test set as we did on the train set to be able to have the same dimensions for the representation of the data. So when I do this, I can see that the test set is slightly smaller than the train set, but I can compute the score. And now I can see that I have, with this model, 89% accuracy. So the split is not the same as done previously, so that's why we don't have the same value. And if I compute the score on the training set, we can see that the model was almost perfectly able to memorize the training samples. So it did not summarize it. It has enough capacity, enough freedom to perfectly memorize the training samples. So we say that this model is not underfitting much, but it's overfitting a bit because there is a difference between the training set and the train set, the test and train set errors. How much time is it? Okay, 5 minutes. We can further introspect the behavior of the text vectorizer. So the text vectorizer has many parameters. So to understand what's the role of each parameter, you can use the docstring. You can call help directly, I think. It's better. You can call help on the class, and you get the docstring of the constructor. and get the explanation for all the parameters. We won't see them all. But you can also empirically evaluate what the TF vectorizer is doing internally by calling this method, build analyzer, that will build an object that is used internally by the vectorizer to do the text preprocessing. And this object that you get back is a configured object that depends on the parameters that you pass to the constructor of the vectorizer, and that is callable and able to process text strings. And you can see that it's taking this sentence, I love Scikit-Learn, column, this is a cool Python lib with an exclamation mark at the end. And you can see that we have individual words that have been normalized. We don't have the capital letters anymore. We don't have the punctuation anymore. So it did some simplification. It's possible to customize this behavior. For instance, you can see that Scikit-Learn, there is a dash here that has been used to split the word. But in this case, Scikit-Learn is more like an individual word by itself. So we can change the token pattern here to say that the dash is a regular letter. And we can also pass a preprocessor, which is the identity function that doesn't do any kind of preprocessing. And in particular, it disables the lower casing. So if I do this and reapply it, we can see that this time I have capital I and I have Scikit-Learn as an individual word. And I have Python with a capital letter.
Would it be good when you're first training it to just make it all lowercase? But
Yeah.
I mean, because this Python with a capital P would be different than just Python lowercase, wouldn't it? Or in a model? Or?
So it depends on the task. For topic classification or spam classification, it might not be important to have the case. So if you lowercase and extract the dimensions, you have fewer dimensions, so less noise. So the model might be better because it has more examples per dimensions. So there are many trade-offs and many parameters, and depending on the task and the size of the data set and if your data set is very noisy, like Twitter, spelling, or stuff from the Wall Street Journal, for instance, all those individual features might impact the performance of the model. So there should be a grid search, basically. So we should do cross-validation of the whole pipeline to find the best parameter. So we'll see later how to do a pipeline. Okay, so we won't do the exercise, but here there's an exercise to write a preprocessor that removes the headers of the post because they have too much information, and we're actually cheating because in the headers of the post we have the name of the sender and the email address. And so we have the university for science guys and stuff like this. So it's cheating, it's not the actual topic. So if we remove the headers, the quality of the prediction is a bit lower, but it's still quite good. We can then assemble the vectorizer with the classifier in an object which we call a pipeline in a Scikit-Learn. So here, make this a bit bigger. Oops. So we are using the passive-aggressive classifier, which is an alternative classifier. It looks a bit like a linear support vector machines, basically, but it's more scalable. And we import the pipeline object, and we will wrap an instance of the vectorizer class and an instance of the classifier here as two specific name steps in a pipeline, the vectorization step and the classifier step. And once we have this, we can call this pipeline directly on the raw data, so the list of Python strings here. And we can train and compute the scores this way. So it takes a bit of time, but the training score now it's 100%, so it has enough capacity to model the complete training set. And the test score is better than what you get with the naive Bayesian classifier. So once you have this pipeline, you can easily tweak any parameter here and rerun the training and evaluation like this. And it's much easier to do model selection, parameter tuning. We'll see later this afternoon, for those who stay for the afternoon session, that we have additional utility function to automatically find the best parameter values from a grid of possible values. Okay, so just 1 minute to introspect the model performance. So I have the pipeline steps here. I can see that in the first step in the vectorizer, I have the feature names, the columns of my representation, my feature extraction, and in the classifier, once it's fitted, I have the coef attribute, which give a weight for each individual feature. So I can take the names of the features, which are the words, and the weights of the classifier, and combine those two to display what are the most important words for my classification per category, per class. So this is a function that wrap this and print the output. And you can see that for the class atheism, the word atheism itself is very important. It's the most important. Atheist is the second one. Keith is very because he must be very active on the mailing list because we have the email addresses and so on. And on the other end, you can see negative values here. For instance, space. Oops, sorry. Space is very negatively correlated with atheism because when you see space, it's from the space category and not. So here you can see that we have a bias because we are not representative of the whole world, but just of our tiny selection of the data. So to avoid those negative stuff, we should add a new class with random text from the internet and to be able to remove those fake negative correlations, basically. So for computer graphics, you can see graphics, image, TIFF, file, and so on. For space, you can see space, orbit, NASA, moon, launch, and so on. And for religion, you can see Christian, Hudson, beast, abortion, biblical, whatever. Won't go into a debate now. You can also report the usual metrics on this pipeline because it feels like a traditional scikit-learn object. And you can also print the confusion matrix and so on, so as usual. Okay, I think it's time to wrap up for this morning session and see you this afternoon if you are courageous, brave enough. Thanks.